In part 2, I mentioned the term chemical reaction. Throughout the rest of this series, I will be using the term sample to describe any material that you may wish to use, such as concentrates from your pan, right down to some of the crushed and pulverized ore that you may want to analyze. When the material that you wish to collect by way of fire assay, this material or sample will be brought to a temperature high enough to melt it. During the melting process, with other reagents, there will be some chemical reactions taking place. It must be understood that when a solid is turned into a molten state, it is referred to as a liquid, better known as a solution. In this presentation, I want to discuss the basic chemistry involved. However, I will not be giving a chemistry course. Just some basic understanding and some basic concepts that you will need in order to calculate the required flux constituents in order to obtain all the precious metals and noble metals, including the refinement of these metals. Welcome back. I'm Rob Boyko, Boyko Mineral Exploration. This may look familiar to you. For all intents and purposes, we can consider the atom to be the smallest particle of a substance. When two atoms or more combine, they become a molecule. Some are considered to be polyatomic. That is to say, they can be treated as if they were a single atom. Some are considered to be diatomic, meaning the atoms form in pairs. Oxygen and hydrogen molecules are diatomic. As depicted here, two hydrogen atoms combine with one oxygen atom, which forms one molecule of water. Each individual atom will have its own characteristic. The difference is in the number of protons and electrons that it has. Each atom represents a specific element, and as you can see by the table, there are many. Too many for me to remember. It is my recommendation to search Google and download yourself one of these tables. It will be a go-to reference when I discuss flux calculations in a future presentation within this series, or message me and I will be happy to send you a PDF copy. Periodic tables will always have an index. The important part of the index, in respect to a small-scale miner or prospector, is shown. This is what will be important to you when we discuss charge equations in an upcoming presentation. The symbol in this example, Ti, represents the name of the element, which is titanium. Another important unit that you must be familiar with is the atomic mass, as well as the ionic charges. These charges are formal electrical charges associated with the element. I will not go into details here as they will be discussed later. Rocks and minerals not only have common names, such as fluorite, they also have a chemical name and associated chemical formula. These are the elements that form the rocks and minerals that are contained in your ores and concentrates. Rocks like pyrite may contain gold and silver in different quantities or concentrations. Galena is not only a good source of lead, but will also contain silver. The point here is that all rocks are basically a compilation of different elements. When we discuss charge calculation in a future presentation, our calculations are based on these elements. There are thousands of different rocks and minerals and a whole lot of formulas. One cannot be expected to remember or even memorize these formulas. I use the Audubon Society's Field Guide to Rocks and Minerals and recommend that you obtain one from your local bookstore. The investment of about $35 is worthwhile as an investment. You will probably use it constantly like I do. The example here is from page 374 from the book. It not only gives the name of the rock or mineral type, but the formula as well as other relevant information and many identifying photographs. I need to introduce you to the mole. It's not that cute little critter that pops out of the ground. It is a concept, like a letter designation in algebra. The mole can symbolize anything. For us, the mole, or written as MOL, represents the atomic weight or atomic mass of a molecule or atom. It can also represent parts of a substance. In essence, as an example, 1 mole of lead has an atomic weight or mass of 207.2 grams. It can also be said that 207.2 grams equals 1 mole of lead. When looking at the atomic mass of a molecule, all one has to do is look up the atomic mass of the elements involved and in the periodic table and add them up. In this example, I am using a simple molecule of litharge, which is lead and oxygen. Oxygen in the periodic table has an atomic weight of 16 grams. Adding them up gives us an atomic weight of 223.2 grams for litharge. Therefore, 1 mole of lead oxide is equal to 223.2 grams. It can also represent parts of a substance. The mixing of hydrochloric acid and nitric acid makes up aqua regia. As shown, it requires 3 parts of hydrochloric acid mixed with 1 part of nitric acid to make 1 part of aqua regia. There will be more regarding the mole concept in future calculations as we progress through the upcoming presentations. There are more than 9 types of chemical reactions. In regards to this fine art of fire, as small-scale miners and prospectors, the types that mean most to us are those that will decompose, combine, combust, displace, precipitate, and one that is a redox reaction. Well, redox reactions are either oxidizing reactions or reducing reactions. This will be discussed in a later presentation. For displacement reactions, there are 2 of them, single displacement and double displacement. Some of these reactions will take place simultaneously during fusion, some during cupellation, and a couple of them during parting. A decomposition reaction is one where the substance decomposes into its individual components. In this classic example, the hydrogen peroxide molecule consists of 2 hydrogen atoms coupled with 2 oxygen atoms. Placing a small amount into a beaker and heating it will cause the hydrogen molecules to split apart and form 2 gases in the form of 1 hydrogen molecule and 1 oxygen molecule. The same would hold true if we just decompose straight water. 2 molecules of water would decompose into 2 molecules of hydrogen and 1 molecule of oxygen. Material can be decomposed either through temperature increase or by dissolving them in a solution of some type. They can also be combined by way of some form of chemical reaction. Without going into a whole lot of detail, I have mentioned those formal charges. When looking at the periodic table, as pictured, the formal charge on the top being +4 is the most common charge of the element, and each charge listed below in sequence are the lesser common charges, and they do exist. These are electrical charges. All base metals have positive charges, and all nonmetals have negative charges. Base metals and nonmetals will be attracted to each other similar to magnets. This is part of the process of a chemical combining, which is termed ionic bonding. Nonmetal to nonmetal bonds are covalent. These would be the sulfates and the nitrates. Covalent bonding is too complicated for the discussion and will not be included. However, you should be aware that sulfate and sulfide have formal charges of 2-. Nitrate and nitrite have minus charges, hydroxide has a minus charge, and phosphate has a 2- charge. Depicted here is a titanium atom which has a +4 charge. Oxygen atoms have -2 charges, And since the product has to be electrically balanced, it takes two oxygen atoms to combine with the titanium atom to produce one molecule of titanium dioxide. When pure magnesium is subjected to heat, it burns with a bright hot flame. The residue is a white powder. This is the product of this reaction. The powder is magnesium oxide. The oxygen in the atmosphere combines with the magnesium by way of an ionic bond, forms this product. It is a form of a decomposition and a composition reaction. Due to the high temperature decomposing the magnesium molecules to individual atoms, and then recombining with the oxygen atoms to form the product. When you burn a log in a fire, the log constituents start to decompose. The log is an organic entity which contains carbon. There will also be a small amount of hydrogen and other constituents. The carbon will covalently bond with the hydrogen, which forms a methane gas. As the temperature increases, the methane will decompose, and carbon will combine with the oxygen in the air to form carbon dioxide and water vapor. Each element has its own reaction characteristic, meaning that some are more reactive than others. Oxygen is more reactive than hydrogen, and hydrogen is more reactive than iron. The least reactive element will be displaced by the most reactive. In this case, with iron sitting in water, eventually the end product will be rust. Rust is nothing more than iron 2 oxide. Since the iron is the least reactive and the hydrogen the second least reactive, the hydrogen will be displaced with the iron, which will combine with the oxygen. If this reaction was left to continue until all the iron and water was consumed, the only products left would be the iron 2 oxide as a solid and hydrogen gas. Similar to the single displacement reactions, the double replacement reactions involve molecular compounds instead of a single element and a molecular compound. Shown here, adding potassium iodide to a solution of lead nitrate, the resulting product is lead 2 diiodide, simply written as lead 2 iodide. Since all substances are soluble in a nitrate solution, the iodine and the potassium iodide will also form an iodide solution. As lead has a low solubility in an iodide solution, it will precipitate out as a solid lead iodide. It can be said that the reaction kinetics of these two compounds does result in a precipitation reaction. Reaction kinetics will not be discussed in these presentations due to its complexity. In fire assay, during the refining stage, which will be discussed in a future presentation, nitric acid is used to remove the silver from a door bead. The result is a form of silver nitrate solution. The silver can be precipitated out of the solution using either sodium chloride or potassium chloride. Since the silver is dissolved in a nitric acid solution, the nitric acid can be neutralized with HCl, or hydrochloric acid, while precipitating the silver as a silver chloride. For simplicity shown here, adding potassium chloride to a solution of silver nitrate, this double displacement and precipitation reaction results in a solid silver chloride, which can be further refined into a metallic silver of high purity. Before discussing the reagents used in the art of fire, I needed to introduce you to some of the very basic chemistry involved. I did not want to make this presentation a chemistry course, but to give you some insight as to what is happening during some of the chemical reactions that occur during fusion, cupellation, scorification, and the parting procedures. In the next future presentation, which will be part 4, I will be discussing or giving some insight into the reagents, that is, the chemical substances that are used in the process. The information given in this presentation will be useful during the next presentation, which is to follow soon. If you like this presentation, please give it a thumbs up. In my channel, I do not try to sell product. However, I do try to promote prospecting and mining for the average individual who may be thinking of trying as a hobby or to infer more information to the small-scale miner or prospector so that you may broaden your horizons and try some fire assay on your own. This channel is strictly for education. I would not feel right to ask for any patronages. My reward would be a like, a share, and a comment. Good or bad. Thank you for watching. I am Rob Boyko, Boyko Mineral Exploration.